Hello guys, I would like to talk about elementary flows and Laplace equation. As known, the Laplace equation can be received from the continuity equation, written as follows. Here, ρ is the density, t is time, u, v, and w are the velocity components, x, y, and z are the geometrical coordinates. To obtain the Laplace equation, we have to make some assumptions. First of all, the flow is stationary, so the time derivative would be equal to 0. Also, the density is constant, and it means that we can exclude it from the derivatives. So our continuity equation becomes the following. To obtain the Laplace equation, we will use a concept of the streamline function or the potential function. The streamline function can be written in the following form. And the potential function can be written as So as we see, the streamline function can be used in the two-dimensional case, and the potential function definition can be used in three-dimensional or two-dimensional case. Now substituting the definition of the streamline function or definition of the potential function, we can obtain the Laplace equation in the following form. In the streamline functions, or same in the potential function. These both functions are called Laplace equation. To remind you the relation between the streamline function and the potential function, I can draw the schematic of the flow. For example, we have a velocity field with known velocity directions, and in this case the streamlines will be formed as the tangential lines to the velocity vectors. These are the different levels of the streamline function. In a similar way, we can define the potential function. As known from the definition, potential function is always perpendicular to the streamline function. So for example, if we define some points and normal direction to these points, we can find the direction of the potential lines. And here, for any line, I can write the following relation, that it's perpendicular the potential function to the streamline function. Mathematically, it is not so much important in which function we are writing our Laplace equation, in the streamline function or in the potential function, because both of them are described by the same equation. Now, going to the elementary flows, we can define the following types of elementary flows explained in the book. The first elementary flow is the uniform flow. Uniform flow is usually described by just one value of the horizontal velocity. The streamlines in this case are always directed horizontally, and in any point in space, the flow velocity is equal to v infinite. In such case, the streamline function is shown by the white line, and the potential function is perpendicular is shown by the green line. Equations for these lines can be found analytically in a very simple way. For any elementary flow, we just need to integrate the flow velocity components and to obtain the streamline function or the potential function. So integrating the constant infinite velocity in x and y direction, I will obtain the following, that my potential function would be equal to v infinite multiplied by x, and my streamline function would be equal to the v infinite multiplied by y coordinate. If you are interested to know how this integration was done, please look chapter 3.9 from the Anderson book. The second elementary flow is so-called source flow. The source flow is characterized by the velocity function written in the following way. Where c is a constant and r is the distance from the center of the source. So this function is hyperbolic. So velocity is having theoretically infinite value in the source and is having zero value in the infinite distance from the source. Integrating this equation in the polar coordinates, because the original velocity is given in polar coordinates, we can come out with the following solution. The potential function would be equal to where lambda is constant value, called strength of the source, and r is the distance from the source in polar coordinates. And the streamline function will be found also integrating the original velocity components as following. In polar coordinates. The main advantageous property of the Laplace equation is that the sum of two solutions of Laplace equation will also form solution of the Laplace equation, so we can summate two elementary flows to obtain the third one. It's called superposition of the uniform and source flows. In such case, we can calculate semi-infinite body. And the streamline function and potential function will be just the sum of two functions of elementary flows. For example, for the streamline function, written in polar coordinates, of course. The summary flow will be equal to the following. As known, the source flow can have a positive and a negative strength when the lambda is positive or the negative value. In case of the negative lambda, it is called the sink flow, when the flow is coming from infinite to a single point. In a similar way, we can say that on infinite distance from this point, the velocity is equal to 0, and at this point, the velocity would be equal to infinite value. When we are combining three flows, an uniform flow, a source flow, and a sink flow, it will be a flow around a Rankine oval. When we approximate point of source and sink to infinitely small distance. Such a flow becomes flow around the cylinder. A doublet with a known streamline function where kappa is the strength of doublet, and when we summate these two flows, we will receive a flow around the cylinder. With the streamline function as a sum of two previous functions. The size of the cylinder or the diameter of the cylinder, as well as the shape of the oval and as well as the shape of the semi-infinite body, can be found always analytically when we are writing the function of the streamline equal to 0. And analytically we can find from this equation theta and r corresponding to this condition. In the case of the flow around the cylinder, this shape would correspond to a circle. Please see more details in the Anderson book. And the last elementary flow we can see in the book is so-called vortex flow. The vortex flow can be described by the following function. where gamma is a constant called strength of the vortex or the circulation, and r is a distance from the center of the vortex. Analyzing this function, we can see that the tangential velocity component will have its infinite value in the center of the vortex and will have its zero value on the infinite distance from the vortex. Integrating this function in the similar way of the previous functions, we can find the following streamline function and the potential function. In polar coordinates. In the table 3.1 of the Anderson book, we can see a list of all elementary flows with known velocity components, streamline function, and potential function. Please let me know if you are interested to know more about elementary flows or some its aspects. I will be always ready to help and explain more these details. Thank you for watching.